What I would say is that relations are important because they generalize. They're important in pure mathematics, certainly. I would also say they're important because they generalize two things that we sort of have immediate applications for. One is functions and the other is directed graphs. Every directed graph can be viewed as a relation. And also a relation is like a more general type of function where you're allowed to have more than one input for each output. You're allowed, sorry, strike that, reverse it. You're allowed to have more than one output for each input. And one of the things we've done in this class is try to search for generalizations. So a relation is a generalization of both a function and a directed graph. Now I'd like to take a moment and let's think about directed graphs. So directed graphs are something that we have lots of. I mean, directed graphs are ubiquitous in representing real world structures. And so one of the things I'd like for us to do is take a few minutes and look for some examples of directed graphs. And since we're doing this class online, you can just drop links or images, links to images. Okay, you can drop links in the chat and we can pull them up and discuss them. So I'm going to give you about 5 minutes to look for some examples of directed graphs. And as you find things you think are interesting, drop them in the chat if you would. You look for examples. Let's look for examples that meet the criteria we looked for earlier, where we go, oh, or where we find ourselves saying, oh, I did not recognize that connection to the real world, but now I see that that's really useful. Does that make sense? Vertices of this, so we're looking at the airline directed graph, and the vertices would be all of the airports that the airline services. And an edge would be a flight between airports. So, you know, I have things like Charlotte, Atlanta. There's certainly a flight from Charlotte to Atlanta. There's a flight from Atlanta to Charlotte. But there's an important piece of information that this is leaving out. Like, is there just one flight from Charlotte to Atlanta? So what we're going to do is we're going to introduce an additional piece of information in this structure, which are edge labels. And I'm going to label each edge with the time. So maybe there's the 6:30 a.m. flight from Charlotte to Atlanta, and then there's a 7:45 a.m. flight from Charlotte to Atlanta, and maybe there's a 8:15 a.m. And I can label each edge with the time. So this is an example of a labeled directed graph, and what we call an edge labeled directed graph, where in addition to the edges, because we have multiple edges and we want to distinguish them, we're going to give an additional piece of each information to each. You need to know what a finite state machine is. And finite state machines are connected to what's called regular languages. Notice they're starting out here with the definition of a relation, and they're also starting out with what's called compositions of a relation. Are y'all with me that the airline directed graph forms a relation? So a composition of two relations is where you kind of do what you might expect. If I have one relation from A to B and another relation that's Q, R, S, T, and then I have another relation, or another set, sorry, that could be X, Y, W. And I have a first relation, which I'm going to call R1. And so R1 is going to be a relation from A to B. Q. So I have XQ, XS, XT, YQ, ZR, ZS. Okay, so this is my first relation. Now I'm going to have my second relation, which is a relation from B to C, B to P. So R2 is equal to Rx, Sy, Sw, and TP. Then the composite relation, if I visualize it this way, comes from following the arrows in any kind of path that I can make here will result in a new thing in my relation, which they are calling composed with R. So here I would have R2 composed with R1 is the set AC such that there exists B such that AB is in R and BC is in S. Except, what did I call this? This is R1 and R2. So I'm going to follow, okay, X goes to Q. That doesn't go anywhere for me. X goes to S and S goes to Y. So in R2 composed with R1, I am going to have XY. And then I look at X goes to T, and then T goes to P. So I'm going to then have XP. And Y goes to Q, which doesn't do anything. Z goes to R, which goes to X. Y'all see what I'm doing? So Z goes to X. Z goes to S, which goes to W. So I also end up with ZW. Are there any that I'm missing? Do I have all of them?
No, we had said that S goes to multiple.
I believe we're also missing ZY. Is this all of them, or are there only 6? Well, this is something when we do these and we realize, okay, maybe this is a little bit challenging. It's a good opportunity to think about. If you were trying to get a computer to do this, how would you? Oh, it's a really good question here.